this sequence shoots off. It is really exponential. It seems almost impossible that we will ever, well, I don't know. It seems almost impossible that we'll ever hit 23. But it could happen. All right, so now to the main part, the main subject of this talk. It has to do with Fermat and Gauss. So there's a classical result. This I should say, is joint work with my former colleague David Applegate, Maximilian Hassler from Martinique, and Chai-Hua Wu from IBM, and possibly others. There's been quite a bit of discussion about this, but most of it has been in discussions with these people. So you remember that in 1796, Gauss wrote in his notebook, Eureka! Triangle plus triangle plus triangle equals none, meaning that every number is the sum of three triangular numbers. And this was a problem that had been around for over 100 years, because Fermat conjectured in 1638 that every number is the sum of three triangular numbers, or the sum, and every number is also the sum of 4 squares, and 5 pentagonal numbers, and 6 hexagonal numbers, and so on. But he couldn't prove any of those claims. And Lagrange is famous for showing in 1770, more than 130 years later, that every number is indeed the sum of 4 squares. And then it took another 16 or so years before Gauss proved that every number is the sum of 3 triangular numbers. And then finally, in 1813, it took quite a long time. Cauchy proved the general case. And so I will use pi to denote the set of palindromes in base 10. And it seems that pi plus this, you can write any number as the sum of 3 palindromes. It seems to be an open question. So let me quickly prove Gauss's result, that every number is the sum of 3 triangular numbers, by reducing it to the 4 squares. The 4 squares question. You know that every number is in fact the sum of 3 squares, unless it looks like 7. 7 is the first number that's not the sum of 4 squares. It's not the sum of 3 squares. And any number, in fact, which is congruent to 7 mod 8 and then times the power of 4 is not. But all the other numbers are sums of 3 squares. Okay, so suppose you want to write n as the sum of 3 triangular numbers. Well, you multiply n by 8 and add 3. Now we have 8n plus 3. That's not a number of the bad kind, so we can write it as the sum of 3 squares, x squared plus y squared plus z squared. And so they're either all odd, the sum has to be odd, so they're either all odd or one is odd and 2 are even. But if one is odd and 2 are even, you can't get something congruent to 3 mod 8. So they all have to be odd. So, now we have 8n plus 3 is the sum of the squares of 3 odd numbers, where you expand them, subtract 3, divide by 8, and you have n is now the sum of 3 triangular numbers. So, starting off with the powerful result, the 4 squares theorem, you can get the 3 triangular numbers very easily. But what about palindromes?
Does Gauss did it?
I don't think so.
That's a better way. Okay.
Well, there are many proofs. How do you write? Give a proof. There are a great many papers. George Andrews has a self-contained elementary proof of the whole of the 3 triangles, but it doesn't make easy reading. There are many proofs.
Well, Gauss knew a lot more. He realized that he was, from all others, had been interested not only in expressing things, but count the number of ways to express it.
Yes.
Gauss realized odd numbers of squares were a lot harder than even numbers of squares.
Yes.
But he he was able to intuit that if you counted the number of representations as the sum of 3 squares, it actually turned out to be a class number, because he was interested in this. And it's much more subtle. The formulas for 4 squares and the like are divisor functions. And then 3 squares involves this really subtle invariant. So he really explored it very thoroughly.
Yes. Yes. But I don't think he looked at palindromes. As far as I can tell, nobody has really looked at palindromes. The first reference I've seen to it is in one of Eric Friedman's puzzle pages. This particular one is from 1997, where he mentions palindromes. And there's a comment on that page that says that John Hoffman checked that for all numbers up to 10 to the 8th are the sum of 3 palindromes. So I looked at the sequence. The number of triples P, Q, R, such that P plus Q plus R is N, where P, Q, and R are palindromes. And the graph of that function looks like this. There's a peak. On the new version of this talk, this is marked in small letters, Mount Benford, because I think this is the Benford phenomenon, that most numbers begin with 1 or 2. And so that's why there's a peak around here. And I think there's probably another peak here that hasn't shown up yet. And when it does show up, it will dominate, and this peak will shrink to nothing. So I think this will be a fractal graph. On the... Yes, now how can I do this? This is sequence number 261422. I want to play this because it sounds pretty good too. And I have... How can I do this? I know. I can do it by playing the talk. Okay, play slideshow. Any of the sequences in the OEIS, of course. So there's the graph. And the reason, Giovanni Resta's name is in the title of the talk because he looked at the number of triples of palindromes, PQR, with P bigger than or equal to Q, bigger than or equal to R, whose sum is N. And of course that's a different sequence, but it has roughly the same appearance. The one I gave seems to be the one that gives a better chance of analyzing it, because it's the cube of the generating function for the palindromes, and which we know explicitly. So I think there's more hope of showing that the coefficients there are always positive than for Resta's version of it. So continuing, there's a statement in this web page of Eric Friedman from John Hoffman, who says that not only did he look at all numbers up to 10 to the 8th and check that they were the sum of 3 palindromes, but he noticed that for all sufficiently large n, you could take one of the 3 palindromes to be the biggest possible, or the next to biggest possible, for all except a finite number of numbers. So I said, well, that's going to be actually just almost good enough for practical purposes. And one practical question is, if you're given a giant number, how do you find 3 palindromes that add up to it? Well, if one of them is the biggest you could hope, in other words, the palindromic floor of the number, that will take away, that will use up. What's left will be about of order square root of n. And what's left will be, if Hoffman is right, will be the sum of two palindromes. And the sum of two palindromes is a much easier question. Unfortunately, he seems to be wrong. But before I knew he was wrong, I said, all right, we can solve this by defining the palindromic order of a number. Order 1 means a palindrome. Order 2 means the sum of two palindromes, but not a palindrome. Order 3 means if you subtract the previous palindrome function, you get something of order 2, something which is the sum of two palindromes. And order 4 means that, so palindromic order 3 means the greedy algorithm works. You subtract the biggest possible palindrome, and what's left is the sum of two, and you're done. Order 4 means that doesn't work, but if you subtract off the previous palindrome before the previous palindrome, that works. And order 5 means all the rest, which according to Hoffman should be a finite sequence. And I worked it out. The smallest one is 101073. And I only found about 20. And I was using Maple, and I did something wrong, unfortunately, because there are actually a lot of these. I asked Chai-Hua Wu for help. And he worked out, he went out to 10 to the something, 10 to the 8th, and he found that there were 500,000 numbers that were not, that were of type 5. That subtracting the biggest palindrome possible didn't work, subtracting the next palindrome possible didn't work. You had to subtract, you had to go down a lot further. And this is the number of order 5 numbers. This is not obviously a finite sequence. So, unfortunately, this attack didn't work, which is a pity.
Are there analogous sequences for other bases? For example, base 2?
Yeah, they looked at all that. No proofs. Base 2 you need 4, for parity reasons. The sum of 3 base 2 palindromes are odd.
Yeah.
All of them. So in order to get all the numbers, 2 isn't enough. 3 will only give you the odd numbers, so you need 4 palindromes in base 2 to get any number. And that's just a conjecture. And if you look at things probabilistically, the reason this should work is that triangular numbers and palindromes are about the same density. The number of palindromes up to n is of order square root of n, just as it is for triangular numbers. So you've got you're taking the sum of a random number of about square root of n plus square root of n plus square root of n. You should cover all the numbers very easily. And so there's a good hope that it would work. A crucial property we don't know is what is the density of the numbers which are sums of two palindromes. We know that palindromes are of density order about square root of n. They are of order square root of n. What about numbers which are sums of two palindromes? I don't have to say that are not palindromes, because the fraction that are palindromes is so tiny we can forget it. So of all the numbers up to n, how many are sums of two palindromes? And Chai-Hua Wu made a graph of the number up to 10 to the 8th, and there's a bump at the beginning, and then it flattens out, and it looks very strongly like it's converging to something about 2/3, more or less. So that's a conjecture. Is it true? And that would imply that the sums of things that are sums of 3, where we really need 3 palindromes, is about 1/3. So we could do a probabilistic attack, just as you do in practice when you're looking at numbers which are sums of trying to write a number as the sum of 3 squares or 4 squares. In the end, you do a probabilistic algorithm. So our attack will be, and we're actually trying to implement this. David Applegate just about has a fast procedure for testing if a number is the sum of two palindromes. So the idea will be, given a huge number, we'll pick a random number underneath it of the same order and subtract it. And with probability 2/3, what's left will be the sum of two palindromes. And if that fails, repeat it. So before too long, it'll work. So here's an example that Chaiwa sent me. It's this number here. It's the sum of three palindromes. And the first one is actually the biggest palindrome underneath it. And when you subtract that off, that eats up. What's left is, of course, a square root of the number we started with. So and what's more, this is a small number, which is the sum of two palindromes. It may not work, but if it doesn't work, repeat. The one nice thing we have is an algorithm, a non-trivial algorithm from Maximilian Hassler for finding out what the palindromic floor of a number is. So if you have a huge number and you want to know what's the biggest palindrome underneath it, it's not so trivial to find it. And so the way he solved this is that he defines a function that I'm calling h here. H of n is you make your number symmetric about the middle, starting at the left. So you make it so that the right-hand half is a mirror image of the first half. So h of 1729 is 1771. H of 96301 is 96369. You just make it symmetric about the middle, you get a palindrome. And now we have an algorithm for finding the palindromic floor. If what you got here is less than the number you started with, that's it. That's the biggest possible palindrome. If not, then it might be a power of 10, which is exceptional, and you subtract 1. Otherwise, what you do is you subtract 1 from the middle digit. So if you've got an odd number of digits, you subtract 1 from the middle digit. So if it was 96301, h of n doesn't work. That's bigger than the number we started with. But if you subtract 1, you get 96201. Now you apply h, and you get 96269, which is less than the number you started with, and the biggest palindrome that you could get. And if it's an even number of digits, you subtract 1 from the digit to the left of the middle, which is very nice. This was not so obvious, in my opinion. So here are three things we would like. We'd like to know the density of sums of two palindromes. We'd like a characterization of sums of two palindromes. How do you tell if a number is the sum of two palindromes? How do you tell if it's the sum of a palindrome of length n and a palindrome of length n minus 1? And of course, we would like a proof that every number. There is a paper on the archive from last year by William Banks from the University of Missouri, who shows that every number is the sum of 49 palindromes. But as far as I know, that's the best known result. One other thing. Suppose you have a sequence with the property that the sum of that any number is the sum of 3 terms. What can you say about that sequence? Well, so what's the least dense sequence with that property? That any number is the sum of 3 terms. So I asked one of my mailing lists, and Veit Elsa provided a very canonical answer. You take numbers, we want numbers that you could, any number is the sum of 3 of them, okay? So take numbers which, in base 3, begin with either 1 or 2, and then you have 2 zeros, and then either 0, 1, 2, or 3, and 2 zeros, and repeat. So out of every 3 terms, digits, you have 2 zeros. So the density of this is this is n to the 1/3. And this works, you can easily check. And here's the sequence A261. And my last remark, second to the last remark, is that it would be very nice if there was a general theorem, a kind of an Erdos-Renyi theorem that said, if the sequence has this property, then when you raise the generating function to some power, the coefficients are all strictly positive. I've seen there's one theorem about a sequence which has the property that any number is the sum of two terms from the sequence. It's an Edo-Schlenny theorem that says if the sequence has such and such a property, then every number is the sum of two terms from the sequence. I don't know, it doesn't apply here, but it would be nice if it did. Let me end up by saying, making my usual appeal that we need more editors. There are a lot of lovely problems that come up, and if you're interested, send me an email. So thank you.